Good morning, students. Myself, Vijay Shankar from EC Department, Chevrolet Engineering College. Today, we are going to discuss about the Fourier transform examples. In the previous classes, we completed what is a Fourier transform and the properties of the Fourier transform, and two examples in the Fourier transformation, and how we can find the magnitude and the phase also. So see the first one, the Fourier transformation examples. How we get the Fourier transform from the Fourier series? Fourier transform. The definition of the Fourier transformation, that x of omega is equal to integral minus infinite to infinite e power minus j omega t dt. I wrote here the f of omega is equal to integral minus infinite to infinite f of t e power minus j omega t dt. And Fourier transform, Fourier series is f of k is equal. See why I am taking the same. F of t is taking here 1 by t, the integral minus t by the t by 2 e power minus j k omega naught t dt. Following my students. See this the Fourier transformation, the Fourier series definitions. X of k is equal to 1 by t, the integral minus t by the t by 2. X of k as a full frequency domain function e power minus j k omega naught t dt. Now the Fourier transformation is x of omega is equal to integral minus infinite to infinite, integral minus infinite to infinite x of t e power minus j omega t dt. Means when the t is multiplied here, class multiplied, the t into x of k is equal to x of omega 1. T into x of k. Here I use the fn and f of omega. The t into x of k is equal to, by comparing the e power minus, instead of omega here the k omega naught is x of omega. Got it, better students? For periodic signals, a discrete waveform is formed, and a periodic signals, a continuous waveform is formed. The inverse Fourier transformation 1 by 2 pi, the integral minus infinite to infinite f of omega e power j omega t d omega. Got it? Now, the Fourier transformation of the signal f of t is defined as f of omega. It is in the form of the magnitude and the exponential function. The definition of the Fourier transformation, f of omega is equal to, and inverse Fourier transformation f of t is equal to, and in the f of omega, the magnitude of f of omega and e power j theta omega is a phase. Okay. So by the application of the Fourier transformation of a signal in time domain is converted into the frequency domain signal. Now the Fourier transformation of any arbitrary signals and the standard signals. The Fourier transformation of the single-sided exponential signal, is exponentially e power minus at, e power minus at, that it is from the 0 to infinite. Why I am saying it is a single-sided, or it is a e power minus at into v of t. In the previous class, we already discuss about this e power minus at mu of t. What is the Fourier transformation? A by the a plus j omega. A by a plus j omega. Don't confuse here. The omega is angular frequency. The omega can be represented as either you can represent omega like this, or it is a omega. Both are the same only. And now it is a double-sided exponential signal. Double-sided exponential signal. So before that, e power minus at mu of t, the Fourier transformation is 1 by a plus j omega. 1 by a plus j omega. And the same, the e power plus at mu of t, exponentially rising and exponentially decaying. E power minus at is a decaying, e power plus at is a rising function. 1 by a minus j omega. A minus j omega. Now, what is the Fourier transformation of e power minus a, the magnitude of t, into mu of t? For all the values, the double-sided, you can take from the minus infinite to infinite. Actually, it is a mu of t when you added, then we can say it is only the single-sided. E power minus at. If all the terms it is multiplied with the a is there, the magnitude is of a into e power minus at. A into e power minus at mu of t is a by capital A by the a plus j omega and capital A by the a minus j omega. Whenever it is a positive exponential, here the a minus j omega. E power minus the negative exponential a plus j omega. Now, what is the Fourier transformation of e power minus of the magnitude of t, Fourier transformation? Means the e power minus here, the t values is left off of the S-plane. So they given the x of t, the signal x of t is equal to some a into the t is negative values e power minus of minus t, means left sided. It becomes of a into e power plus at. E power plus at. It is from minus infinite to 0. The range is minus infinite to the 0. Similarly, the same signal x of t for the right sided e power minus a plus t. E power minus a plus t is some a into e power minus plus is a minus only, minus at. It is from 0 to infinite. 0 to infinite. Find the Fourier transformation of this signal x of t is equal to. They got the definition of the Fourier transformation. Fourier transformation, integral minus infinite to 0. So what is the exponential here? E power at. E power at. A is also there. A plus a into mu of, not the mu, dt. Plus, for this also the function is a is multiplied a into the 0 to infinite e power minus at dt. Okay. Now you can take e power at integral is e power at by a. E power at by a. Not it is only the given signal, my dear students. Something went wrong here. E power at is a signal. As per the definition of the Fourier transformation, e power minus j omega t is also multiplied. e power minus j omega t for both the functions. So e power t is taken as a common. T you can take as a common. It becomes of a minus j omega by a minus j omega, with upper limit is 0 and lower limit is a minus infinite. A is multiplied for the two functions, so I am taking the common, plus here e power minus t can take as a common in the row for the functions because the bases are same. A plus j omega, a plus j omega by a plus j omega, and take the limitations here, infinite and the 0. Infinite and 0. For the first term, anything power infinite is a 0, and here for the second term, the upper limit is anything power infinite is a 0. So a into 1 by a minus j omega, 1 by a minus j omega, plus the second term is a 0 here, and in this the first term is a 0, second term is there, that is a minus 1 by a plus j omega, a plus j omega. Now take the LCM here, a plus j omega and a minus j omega, that is a square minus b square, minus b is j omega, j square is a plus, so a square plus omega square. So a plus j omega in the numerator, a plus j omega minus a plus j omega. So plus a minus j get cancelled. Finally, we get 2j omega by a square plus omega square. This is the Fourier transformation of e power minus a, the magnitude of t. Fourier transformation is 2j omega by a square plus omega square. Got it, my dear students? This is e power minus at and the Fourier transformation of e power plus at, with a is a magnitude and here is a is also there. So a into e power minus here the magnitude of t. A into 2 j omega by a square plus omega square. Got it? So we got the same thing, the 2a by, and because we have the minus is there in this, and this is becomes a plus. The value is a plus, and these two are get cancelled. A is a 2a. A is a 2a. Capital A into 2a. Got it? And next one is the Fourier transformation of a constant x of t is equal to a. X of t is equal to a value. The definition of the Fourier transformation directly applied, the constant will not satisfy the condition. One of the discrete equations is not absolutely integrable. The integral minus infinite, the magnitude of x of t dt is less than the infinite. Let x1 is a double-sided the signal. x1 of t is equal to a into e power minus at minus a into the magnitude of t. And for that function, we got the 2a by the a square plus omega square. The capital A is the magnitude. We got here itself the same thing, the 2a into 2a by a square plus omega square. And omega is equal to 0, the above equation represented as an impulse of the magnitude of k. impulse of the magnitude of k. The omega is equal to 0. 0 means 2a capital A by a square and a get cancelled. We have to get the constant one. 2 by a. The magnitude of k can be evaluated as k is equal to minus infinite to infinite 2a into a the omega square plus a square into d omega as of the inverse Fourier transformation. And since from the integral 1 by a square plus x square is a 1 by a into tan inverse x by a. By using this relation, you can write it as the same thing. The k is equal to as a k we can take as integral minus infinite to infinite 2a into capital A by omega square plus a square with a d omega. Using this integral dx by x square plus a square, dx by x square plus a square, the d omega here, omega square plus a square. 2a capital A, 2 small a capital A is a constant, and it is an integral minus infinite to infinite 1 by omega square plus a square into d omega. So 1 by a tan inverse omega by a, the upper limit is plus infinite and the lower limit is a minus infinite. When you can substitute the upper limit, it becomes of pi by 2 and lower limit is a minus pi by 2 because tan inverse infinite is a pi by 2 and tan inverse minus infinite is a minus pi by 2. So 2a into here the 2a small a into capital A. Forget about the capital A is there. There is a magnitude only. When it is a magnitude here like and what is the remaining term? 1 by a into pi by 2 minus 1 by a into minus pi by 2. Okay, for the lower limit you can substitute. 2 into a pi by 2 minus of minus pi by 2 pi by 2 minus and here the 2a is there, 1 by a, let's also take the common and we'll get the pi. Pi by 2 plus pi by 2 is a pi, a get cancelled. So 2 pi a, 2 pi a. So the Fourier transformation of constant is 2 pi into delta of omega. 2 pi into delta of omega, the Fourier transformation. The constant a is a and its Fourier transformation is 2 pi a into delta omega, 2 pi into delta omega. Or you can use the Fourier transformation of 1 by using the duality property also. The duality property. So what is the duality property? Saying that x of t is equal to x of t, not the t is equal to x of t. The Fourier transformation is 2 pi into x of minus omega. 2 pi into x of minus omega. So the Fourier transformation of 1, what is the Fourier transformation of 1 is the 2 pi into delta of omega. 2 pi into delta of omega. Now by using this property, the duality property, the Fourier transformation of 1, according to the definition of the Fourier transformation, x of omega is equal to minus infinite to infinite x of t e power minus j omega td. But it matters. That is equal to integral. I need to the Fourier transformation of 1 means x of t is equal to 1. 1 e power minus j omega t dt. It is a minus infinite to infinite. So integral minus infinite to infinite e power minus j omega t dt. The x of omega is equal. X of omega is equal to. Okay. Means see here the integral minus infinite to infinite e power minus j omega t dt. Apply the integral for this one. And it is not the less than the infinite. It's not the absolutely integrable. It is not satisfies the condition. So you're not taking from the minus infinite to infinite the e power minus j omega t dt. It is not at all the less than the infinite. So indirect method, that is the x of t, the Fourier transformation is 2 pi into x of minus omega, x of minus omega. Is the interchange of the signals, interchange the omega as t and the t as omega, getting x of t, the Fourier transformation of the 2 pi into x of minus omega. And this x of minus omega is considered as a delta of omega. Delta of omega, either delta of omega or delta of minus omega. Only one signal. The delta means having only at the 0. So let us take it as a delta of omega. At omega is equal to 0, the value is a 1. Even if it is a delta of minus omega is also, the folded function is the same. Folded function is the same. So x of t, the Fourier transformation is x of omega. And I'm taking the x of t, Fourier transformation is x of omega. But here there is a 1 is there. 1, the Fourier transformation is a 2 pi into the x of minus omega. So both are the same. So it is becomes of 2 pi into delta of omega. 2 pi into the delta of omega function. That we can get from the duality property also. Remember that the Fourier transformation of constant is a 2 pi into delta of omega. And the Fourier transformation of the step function. Fourier transformation of the step function from the signum function. So you know the signum function look like signum of t. Signum of t, the Fourier, not the Fourier. For the positive relaxes, the value is a 1. For the negative relaxes, is a minus 1. So signum of t in terms of the step function is 2 into mu of t minus 1. 2 into mu of t minus 1. So mu of t is a 1 for positive value. The 2 into 1 minus 1 is a 1. For mu of t, the negative values is a 0. 2 into 0 minus 1, it is a minus 1. Okay. Now I need the Fourier transformation of the step function. So what is it? To mu of t is equal to signum function, signum of t plus 1 is equal to 2 into mu of t. 2 into mu of t. Okay. So mu of t is equal to 1 by 2 into 1 by 2 into 1 plus signum of t. Got it, my students? 1 by 2 into 1 plus signum of t. And now I need the Fourier transformation of mu of t. The Fourier transformation of mu of t is equal to, in the right hand side, the Fourier transformation of 1 by 2 plus, and this 1 by 2 is also for the signum, 1 by 2 the Fourier transformation of signum function, signum of t. Okay. And rewrite the left hand side equation, 1 by 2 the Fourier transformation of 1 and 1 by 2 the Fourier transformation of the signum function, signum of t. Okay. So what is the Fourier transformation of 1? We got 1 by 2 into Fourier transformation is a 2 pi into delta omega. 2 pi into delta of omega plus 1 by 2 into signum of t. What is the signum of t? The Fourier transformation is because it is a value is 1 for positive values and the negative value here. The signum of function is a 2 pi by j omega. the 2 by j omega. So finally, the 2 get cancelled here. That is a 2 get cancelled. Pi into delta of omega plus 1 by j omega is a Fourier transformation of mu of t by using the constant of 1. 1 by j omega actually is 1 by j omega, only the mu of t. Or the signum function, how it is getting is 2 into 1 by j omega. It is a mu of t is 1 by j omega only. So directly you can find out the mu of t. Directly you can find out the mu of t for minus j omega t dt. The integral minus infinite to infinite. Mu of t is a 1 from the 0 to infinite. 0 to infinite e power minus j omega t dt. We can directly apply this e power minus j omega t by minus j omega with upper limit is infinite and lower limit is 0. When I substitute the upper limit, infinite is e power infinite is a 0 and lower limit e power minus 0 is a 1, and here already the minus is a minus into minus is a plus. 1 by j omega 1 by j omega. Got it, my students? When I am not considered, that is a Fourier transformation of 1 here. It is a 2 into 2 by the j omega only, simply the Fourier transformation of the signum function. And whenever it is a Fourier transformation of constant, we have the 2 pi into delta omega is there. The mu of t is changes as pi into delta omega plus 1 by j omega, and the signum function is also is 2 by the j omega. Got it? And the Fourier transformation of the sinusoidal signal. Fourier transformation of sinusoidal signal. We know the sine omega naught t. Sine omega naught t is e power or sine omega naught t is equal to e power j omega naught t minus e power minus j omega naught t by 2j. You have to find out the Fourier transformation of this function, and 1 by j or a is also there. They given the a by 2j can take as a common here, and the e power j omega naught t minus e power minus j omega naught t, and apply the Fourier transformation on both sides. The Fourier transformation of a sine omega naught t, a sine omega naught t is equal to a by 2j is a common, a by 2j into the Fourier transformation of the Fourier transformation of e power j omega naught t minus the Fourier transformation of e power minus j omega naught t. Okay. Means here the Fourier transformation of e power j omega naught t is a 1 by 2 is there. And before that there is a 1 by 2. Let us take the Fourier transformation of e power j omega naught t. Means take on the definition of the Fourier transformation, x of omega is equal to integral minus infinite to infinite. And you can substitute the e power j omega naught t into e power minus j omega into t dt. That is equal to integral minus infinite to infinite e power. Take the common of the j minus j, you can take the common. We'll get omega minus omega naught into t dt. Means is a let us assume the e power minus j omega t only. There is a 1 here. What is the Fourier transformation of 1? Fourier transformation of 1 is a 2 pi delta omega. Got it, my student? 2 pi delta omega. What is the omega here? Instead of omega here, the omega minus omega naught. So x of omega for this function, the 2 pi into delta of omega minus omega naught. This is a Fourier transformation of the function. A by 2j into, this is a Fourier transformation of e power j omega naught t is a 2 pi into delta of omega minus omega minus, and here the minus is there, definitely we'll get the 2 pi into delta of omega plus omega. So here the 2 is, take the common, 2 to get cancelled. Finally, the Fourier transformation of a into sine omega naught t is equal to a into sine omega naught t is equal to pi delta of omega minus omega naught minus pi delta omega plus omega naught by j, and the a is also there. This is a Fourier transformation of the given function. See here, a into, this is a value, a into pi by j delta omega minus omega naught plus delta omega plus omega. As of the given signal is a sinusoidal signal, the frequency, the time domain is a sinusoidal signal, the frequency domain signal is a pi into delta of omega minus omega naught and pi into delta omega plus omega. Got it, my students?